Right, our next talk is by Martin Houde, and he's going to tell us about dispersion of magnetic fields in molecular clouds, analysis of interferometry data.
Okay, can you hear me? Sorry? No. I'll hold it. Okay. So first I'd like to thank the organizer to allow me to talk about some recent work I've done with the people were listed there. Right here. There's Chad, Dick, and my old friends with whom I worked on this subject for a long time, John Vaillancourt and Roger Hildebrand. Okay, so dispersion of magnetic fields analysis. So this is all rests on structure functions or related functions. So I'm not going to spend much time on this as it's been mentioned several times. So what it consists of is basically take a polarization map, look at differences in orientation between polarization angle for different lags, and then calculate the structure function. You also assume that the magnetic field is composed of a turbulent and a regular or ordered or large-scale magnetic field, and that these two are on separate scale. They evolve in separate scale. And then when you look at the structure function, it also breaks down into those two components. One caveat is that I don't actually use the structure function. I use this thing here, which I call the dispersion function, which is just very related to the structure function for small differences in angle. And it'll become clear, I hope, why I do this. Well, for one thing, this function is related to the autocorrelation function of the magnetic field, which will be useful later on. Okay, so the first example we did many years ago, in 2009, we used an Orion map obtained with Giles polarimeter of the CSO, or the sharp polarimeter. And if you look at the magnetic fields here, the orientation magnetic field, gain from polarization. So what you do, you effectively translate your map in a given direction by a given lag, and you do that for many different values of lags, and then you calculate your function, and you get this. What is this? Well, this is the dispersion function here, as a function here at the top of the lag squared. The reason why we do that is that it's often easier to see the difference in scale between the large-scale component and the turbulent. So the symbols here are the data. The solid line is a fit. So one of the nice things about this function that I was talking about, the dispersion function, is that you can actually have exact solution for some model of turbulence. You can analytically calculate them. And that gives you, by analyzing the data, as I will show, some quantitative measurement of some key parameters. The model is that solid line, as I was saying, and one thing it tells you is this broken line here is actually the large-scale component of the dispersion function. So here it's the same thing, but now it's as a function of L instead of L squared. So now what you can do is you subtract the data from that large-scale component, and what you're left with here is the normalized autocorrelation function of the turbulent component. Okay? Now, this autocorrelation function is actually broadened by the beam. So what I put here, this broken line, is actually the autocorrelated beam. So what you see is that much of the correlation you see is actually due to the beam. But the extra that you get here between the beam and the data, that's a signature of turbulence. This is a measure of the correlation scale of the turbulent component of the magnetic field. This point here that you have there is the energy content in turbulence in the magnetic field, and that's what you would take 10 years ago. You would have take the square root of that and put in the Davis Chandrasekhar-Fermi equation to get the magnetic field strength. But the model now gives us D, delta, the correlation length, and because you know delta, you can actually, the model turns out that it can extract the actual value of the turbulent energy in the magnetic field. So what I mean by this is this. So for OMC1, we had a correlation length of 16 milliparsec, which implies then, because you know your beam, that you know the number of turbulent cells that are in your beam. In this case here, we had 21. So that this energy content you saw before from the data, straight from the data, appeared to be about 1.3%. But now if you correct for the integration in the beam of those 21 cells, what you find is actually there's a whole lot more turbulence. You've got 30%. You went from 1.3 to 28%. So of course, it's very tempting to take these values and throw them in the DCF equation, and then you can measure magnetic field. In this case, we got about 800 microgauss. Now, if we had not taken into account the integration, we would have gotten something, well, this value times the square root of 21, which is about 3.5 milligauss. Okay, so it's a big correction in this case. So that was the first example. We published that in 2009. Before I jump into the interferometry data, I'll just quickly say that you can actually do a lot better if you have a lot of data, a lot of vectors. So in this case here, what we did, we took synchrotron polarization data for M51 that Andrew Fletcher made available to me, and we worked on this. And there we had so many vectors that we actually did not assume isotropic turbulence. We actually went and looked for anisotropy. So you can generalize the model and look and have a anisotropic turbulent model. And that allowed us to measure a signature of anisotropy. This is a contour map of the autocorrelation function with the beam and without the beam. And then we saw clearly that the correlation length was about a factor of 2 longer along the magnetic field and across the mean magnetic field locally. So that was a clear signature of anisotropy. So you can do things like that if you have lots of statistics. Okay, so let's jump in now into interferometry. So here's a map obtained with CARMA, TADPOL survey, resolution of about 3 arcsecond, W3OH. And you'd like to apply the same technique to data like that. But the problem, and it's something that we discussed in a paper in 2011, the problem is that the model that I just showed you applies to single dish data, not to interferometry data. If you apply that, well, certainly at the time we discussed it, we didn't know what the errors would be. The problem is this. So what is this? This is frequency and spatial frequencies. And what you see here, this broken line, is the dirty beam, the spectrum associated with the dirty beam. So you can see for an interferometer, it goes to 0, so large scales are filtered out, okay? And that is a problem because that's where your power spectrum of turbulence peaks. So if you try to apply something, a technique or a model that does not take that into account, you may have errors. But it dawned on me a few months ago that I could easily extend the model by doing the following. So this other line here is the spectrum of the synthesized beam that comes in with the interferometry data. And what I did is I subtract, and so this usually is a Gaussian, I subtract another Gaussian here to take into account the filtering and low frequency. And then you can again get an analytic form for the solution. And then you can have an augmented model and apply it to the data. So here's what I do. Again, dispersion function is a function of the square of the lag. You see very well here the large scale component, the small scale component due to turbulence. The model, the blue line here that hopefully you see is the fit to the model, the fit to the data with the model, which is very good in this case. The broken line again is the large scale component that doesn't really hug the data as before, and that's a consequence of this new model that takes into account the filtering of the data in frequency space. You subtract the data from the large scale component, you get, again, the autocorrelation function of the magnetic field, and you measure once again delta, the correlation length. In this case, we did that actually for three sources. The one I was discussing is W3OH. The result of the analysis are as follows: about 10 to 20 milliparsec for the correlation length of the turbulent magnetic field. You can measure and we found that there's a lot of energy in turbulence in the magnetic field, so between 60 and about 75%, so a fair amount of turbulence. And then again, if you use the DCF equation, we got, in all cases, something around 1 milligauss. But as was said before, this is the ALMA era, at least the start of it. So Chad was kind enough to give me his Serpens data that he presented today. Now we have a resolution of about 10 times what we had before. So when I see something like that, I say, we're going to be able to do a lot more than before. So here's the analysis. Same thing as before. The model fits very well. We got the autocorrelation function, and now we have a big delta. You can see that relative to the beam, we have a much higher resolution. The beam is small, and we measure delta. But delta is not 10 to 20 milliparsec anymore. It's only 1 milliparsec, which is unfortunate. I thought it would be about the same thing. Then we could do a whole lot more that I will tell you about just now. What I thought we could do more is this. Because I use this function here for the dispersion, which is the autocorrelation function, that implies that if I just take a Fourier transform of that thing, I get the power spectrum. More precisely, what I get is the power spectrum of turbulence filtered by the beam. Okay? So in principle, if I have high resolution, like in this case, I should be able to deconvolve the beam and get to the power spectrum, which would be a good thing to do if you want to study magnetized turbulence. So here's the Fourier transform. So at the top here, spatial frequencies. The points here are the power spectrum that are filtered by the telescope beam here. This is just about to die. But so now what do? We remove the beam, and then the data here in the middle are now the deconvolved power spectrum. The width of the spectrum is proportional, thank you very much, is proportional to the inverse of the delta, the correlation length we measured before. And then you can play another trick. You can multiply these data by 2 pi k to get a Kolmogorov-like power spectrum. And then you can plot it in a log-to-log fashion, as is usually done. And you can do things like fitting a power law in the perhaps inertial, oh yeah, no, I need this. Okay. You want me to do that? Yeah, if you want to, perfect. So, and what I was really hoping with having the increased resolution is that I would be able to see and measure some diffusion scale at the high frequency end. And at first look, you think that, hey, maybe we got it. But looking at it carefully, and now we're still early in the game, I don't trust these data. These points are about 2 orders of magnitude lower than maximum, and we're at the point where a systematics in the data processing comes into play. So I don't believe these things here. Okay? Why is it that I don't measure it? The problem is that this ALMA data, because of the filtering, probe much denser material than what we did with CARMA. With CARMA, we had 10 to the 6 roughly per cubic centimeters. Here's it's 10 to the 7 and more. And therefore, if you look, for example, something like the ambipolar diffusion length scale, which decreases with increasing density, this is why we don't see it. Okay? So I'll just put my summary and I'll take any questions. Thank you.
All right, questions for Martin? Yes, Dick.
I wonder, with your more sophisticated technique, if you could briefly discuss what you think the uncertainty in mean fields inferred from these kinds of data might be.
Sure. Were you the referee in the paper?
No?
So in the original version of the paper, I'd written the factor of few for the magnetic field strength. The referee put their foot down and said, now I want a number. So I started thinking about all the processes, all the values that you put a number in the DCF equation. And I don't think it's better than factor of 3. So when I say 1 milligauss, it could be 0.4, it could be 3, I think. There's a lot of uncertainty. So that's without talking about the uncertainty related to the DCF equation itself when applied to these systems. So we need to, Chris was telling me last night, so what we need to do is to do a lot of measurements and get some statistics, and hopefully these factor of 3 will cancel out.
Okay, so a question, Paulo?
So how far in resolution, I mean, in angular and length scales, do you think that we have to go?
Well, it depends. I think what we have to do is to be a little bit smart about it. So go to higher resolution. This is 0.3, so you can go much better, right, with ALMA. But also, we have to have, with the sensitivity ALMA, is move away and go more in the more diffuse stuff, not right in the center where you have those big bright sources, but move a little bit away from that to bring down the density. And hopefully, then this diffusion scale will move it to lower frequency than we can see it. That would be really interesting. If you can measure this parameter, then you have a handle on it.
Perfect. Very quickly, go ahead, Alex.
What is the model that you subtract? I was confused.
So the model, the analytical model, so we use an idealized Gaussian turbulence, the autocorrelation function of the turbulence we assume
But
is
you
Gaussian.
have some slope of this.
That's right.
How
So
do you define it?
That's just we fit a Taylor series to low power, the first few terms of the Taylor series to this. The good thing with that is that we don't need to have some model like an hourglass or something to subtract. You just see it in the large scale and you remove.